Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 15th lecture on materials for maritime structures. In this lecture, we are going to talk about steel as one of the promising and commonly used material for maritime construction. We know most of the old maritime structures like port and harbors are constructed with concrete and rubble masonry. However, when you start moving towards form dominant designs, steel has dominated the construction segment of maritime structures. So steel is a very most preferred material for construction of maritime structures for several reasons. The foremost engineering attraction steel has is its ductility and high strength by alloying it with different metals. So, high strength and huge ductility possibility in steel enables it to be the most preferred material. So, in this lecture 15, welcome to understanding more details on materials for maritime structures, section 2 under the SwayamPrabha course offered by the Department of Maritime Engineering, IIT Gandhinagar. The title of the course: Maritime Structures, Types, Construction, Pre-Service Analysis and Design. Friends, steel can be alloyed to modify its characteristics, that is engineering properties, and to suit its requirement for offshore platforms where strength and stiffness are equally necessary for counteracting the loads acting on these kind of structures. The foremost idea being the weight reduction, because in offshore structural systems, which are essentially subset of maritime structures, payload plays a very important role in ascertaining the functional value of any structural system constructed offshore. So, if we are able to get a weight reduction in the design with higher strength and stiffness, then we prefer that kind of alloys of steel for construction of maritime structures. Furthermore, friends, it is very important for us to realize at this point that corrosion resistance, high tension strength are few factors which are closely dependent on the alloying material, the percentage carbon present in the alloying metal, and then the type of manufacturing or heat treatment. One can modify these engineering properties of corrosion resistance and high strength factors by simply alloying steel with different metals of different composition and percentage. Two common examples which are very popular in maritime structures is low alloy and high strength alloy. Let us speak something about the low alloy steel. It is usually iron based alloy that is hardened to gain the higher strength. A common steel alloy has a strength in the range of about 1200 megapascal. Just to reiterate, megapascal is actually 10 power 6 Newton per meter square, which is 10 power 6 into 1 by 10 power 6 of Newton per mm square. So, megapascal can be also strictly seen as Newton per mm square. So, usually steel has a strength of about 1242 Newton per mm square up to about 1400, which is referred generally as AISI 4130 steel grade. Another type of AISI 4340 is also commonly used in maritime construction, where its strength ranges from 1400 to about 1900 megapascal. Whereas you see the commonly used structural steel in land based construction is about 450 to 600 megapascal, is it not? We use Fe 415 or Fe 500 and so on. So, we are talking about steel which is at least 4 times stronger. Friends, it is because of this reason maritime structures are sleek and elegant. At the same time, the weight reduction plays a very important role compared to its higher strength and corrosion resistance. When we talk about high strength alloy, it is a family of 300 M whose strength can exceed 2000 megapascal. It can cross about 2000 Newton per mm square. This family of steel has a very great disadvantage. It is very corrosion prone and must be electroplated to avoid corrosion. So, strength and corrosion, they do not go together. When you have got an alloy, to increase its strength, the composition of alloying elements also contribute to corrosion. Therefore, if you have got a high strength alloy in place for design, then one should take care of corrosion protection measures. One important application is electroplating. Therefore, friends, before we choose steel for maritime construction, we have to see how they are classified. Let us see how steel is classified. One may ask a question, what do we understand by classification of steel? The moment we say steel, it has got an yield strength and Young's modulus, that is all. What is classification? Now here comes the difference. In maritime application, you have got a wide variety of steel composition. What I can say as alloy, which can be chosen for different types of structures. Number 1. Number 2, even within a given structural system, a structural member can be of different steel. For example, in maybe a jacket structure, we can use different steel for bracings and different steel for columns and different steel grade for deck. So, even in a given structural system, different members can also have different grades of steel. So, in that case, we have to grade steel based on its application, and there are some factors which will govern or which will help us to classify steel. So, therefore, steel classification becomes important. Now, steel can be classified in many ways. 1, it can be based on composition. Examples could be carbon steel, low alloy or stainless steel. It can also be classified based on manufacturing methods, electric furnace method, open hearth method, basic oxygen, etc. You can also classify steel based on its finishing, hot rolling or cold rolling, based on its product form, which we already know: bar, plate, sheet, strip, tubes and structural shapes of channel, angle. This is what we know very well as classification of steel based on its geometric product. Steel can also be further classified, friends, based on the microstructure as ferritic, perlitic and martensitic. Based on strength level required, different standards of codes of practice will also give you different grades or classification of steel as class A, B, C, which we will see in the coming slides. Steel is also classified based on heat treatment like annealing, quenching and tempering. So, friends, there can be a composition within this to form a group of steel. So, for example, a low carbon steel can also be manufactured using annealing or quenching and tempering to increase its strength. So, the properties of steel can be also varied depending upon how they are finished, how they are manufactured, what microstructure is being used and so on. So, this is a very interesting area where upcoming research of advanced classification based on materials engineering and materials perspective is also one of the subsegment of maritime structures. So, friends, steel can be classified in about 8 ways. So, it is not that simply you say steel, you have to specifically say what kind of steel, what classification of steel, what subclassification of steel is being used for maritime structures. Having said this, let us quickly elaborate and see based on strength how can we classify steel, because we already said that based on strength different codes classify them in a different manner. So, based on strength they can be classified as low, medium and high strength steel. The moment they say low, how low it is? It is about the yield strength is lesser than about 415 megapascal. They are usually used for hull structures of ships, fittings, tank instrument fittings and buoys. You know, when steel is being classified based on strength, it is very interesting, friends, to understand this classification is also related to its possible application on structures. We have never heard this kind of classification based on application to structures in conventional structural engineering or in material science. Is it not? Because in structural steel, we never classify steel based upon whether we are going to use the steel for a beam or a column or a foundation or a gusset plate or a girder or a truss element or a bracing element. We never classify them. Classification is disconnected from its application perspective in structural construction in land. Whereas, when you move to offshore or maritime structures, classification is also recommended based on its type of application. This is a very interesting news which one should be able to get attracted in material science applications in maritime structures. So, load strength steel are generally used in constructing hull forms of ships and other places, as you see on the screen. Medium strength of steel varies from 415 up to 1035 megapascal. They are generally used for icebreakers and buoys in Arctic region. You have buoys here also, but this is in Arctic region. High strength steel is a steel of higher yield strength which is greater than 1035 megapascal. Maraging steel is one CADA which has got 2 GPa strength, where it is being used under special applications in offshore structures like subsea mining, okay. Then wave energy harvest, power takeoff mechanisms. We have already seen them in the previous lectures. I hope you will recollect them. So, classification of steel also helps me not only to classify them based on strength, but also based on their application. That is a very interesting news what we have learned. Let us see, based on tensile strength alone, how can you group steel? Friends, I am now talking about another subclassification which is grouping of steel. You can also group steel as 1, 2 and 3, whereas group 1 has yield strength lesser than 275 megapascal. Group 2 is between 275 and 415, and group 3 is lesser than 690 and exceeds 415. ABS, American Bureau of Shipping, helps us to give this classification based on the yield strength alone, that is the tensile strength. Okay. Look at this table. Let us say group 1 steel whose tensile strength or yield strength is less than 275 megapascal are all classified as a specific grade of ASTM A3694, for example, ASTM A13194 and so on. So, these are all steel grades. So, you can see there are so many grades of steel available in classification 1 or group 1, 2 and 3, which is quite interesting. Secondly, what you must understand is, it is an extract we have taken from the code for our dissemination of knowledge. They are based on two things, one is tensile strength, other is yield strength. Okay. One can see that group 1 yield strength are given, group 2 yield strength can go as high as 485, or let us say even it can touch 690, no 485 or 620. Exceeding that becomes group 3, where it can go as high as 690. Also, please note, the grouping based on yield and tensile strength also refers to thickness. Okay? Thickness of the metal being used for construction. If it is up to 50 mm thick, you have a different grade. From 12 to 25 mm thick, you have a different grade. So, steel is also subgroup based on its thickness. We have never seen this kind of classification of steel in structural steel forms used in land based construction. That is a new technique what offshore or maritime industries follow. Now, let us ask another question to ourselves as maritime engineers. What are the fundamental requirements of material selection? So, if you want to select a material for construction in maritime engineering or maritime structures, what are the fundamental requirements? 1. Formability, weldability, strength, toughness and corrosion resistance. These are all essential requirements, fundamental requirements of any material to be chosen for maritime construction, not only steel. However, when we talk about steel, they are all directly applicable and they are very useful. Amongst this, we talk about one important requirement, which is toughness. Why I am requesting you to watch this? Because again, based on toughness, the recommended application of steel classification is also done in codes. For example, a steel with a specific range of toughness cannot be used for substructure. A steel with an advanced range of toughness can only be used for columns and buckling members. So, this kind of recommendation, more engineering perspective is there in maritime structural design. So, before we do the design, we need to understand the material requirement very carefully. Let us take about one elaborated understanding about toughness. Please pay attention to this particular slide, friends. Toughness generally is expressed based on Charpy's toughness. Based on Charpy's toughness, steel is again grouped as 1, 2 and 3 as we earlier saw. When you want to group them based on Charpy's toughness index, then Charpy's test need to be conducted. That test can be conducted only at a service temperature of about 30 degrees. Okay? The service temperature, it should be 30 degrees below the minimum service temperature, whereas the service temperature for members below splash zone is 0 degree. You know what is a splash zone? Let me try to draw a figure. We already said that, but still we reiterate that. Let us say I will draw a TLP. These are column members, these are pontoon members, this top side of the deck, and deck will have the drilling derrick. It can even have the helipad, can also have the living quarters, and these are teethers which are anchored to the seabed. Axial initial pretension. This is my water level, still water level, and I can mark the water depth as small d. So, these are teethers, otherwise called as tendons. These are column members, and this is called pontoon member, and this is an axially pretension cable. Okay, axially pretension. Okay, so this is a typical TLP. Okay, now the region closer to the mean sea level, the region closer to mean sea level is called splash zone. It is in this zone the corrosion is maximum. It is in this zone the corrosion is expected to be maximum. So, friends, splash zone is the indicator where the corrosion is maximum. Therefore, when I want to use steel which is a corrosion sensitive element or structural element, I must be careful in choosing the thickness of the member which is kept in the splash zone. So, based on such requirements, the steel is also classified. So, let us look at the toughness part of how the steel is chosen. When you talk about toughness, one important test which ascertains toughness is Charpy's impact test. Charpy's test helps us to classify or grade steel or group steel into 1, 2, 1, 3. So, we have been seeing steel classification based on methods of manufacturing, microlith structure, etc. We also saw grouping based on yield strength. Now, we are seeing grouping based on Charpy's strength. It is very interesting and very detailed as far as elements chosen for maritime structures are concerned. Steel as such is not being recommended for design. We have got to specifically say what group, what classification, what yield strength, what Charpy's impact number and what corrosion resistance, etc. There are many associated properties required to be specified if we want to recommend steel for maritime construction. So, look at this particular table which is again extracted from the code, saying that based on Charpy's toughness specification for steel, steel is grouped as 1, 2, 1, 3. So, if you look at the table very carefully, the energy absorption longitudinal sector in joules is given. So, for thickness varying from 6 to 19 millimeter, in terms of inches also is given, but we will focus on system international units. So, in terms of thickness varying from 6 to 19 millimeter, you will say that the energy absorption required by Charpy's test is about 20 joules. If the thickness exceeds 19 millimeter, then the Charpy's demand is 27. If the thickness exceeds 6 millimeter in group 213 steel, then the Charpy's demand is 34. However, friends, you conduct Charpy's test at a specific temperature. Okay? The test at which this temperature is conducted is 30 degrees below the minimum service temperature, friends, because the service temperature varies depending upon the location of member in offshore. As you go deeper, temperature freezes. As you go above, it becomes relaxed. So, the members are subjected to differential temperature as well. So, one must be very clear in ascertaining the Charpy's impact or Charpy's toughness based on the temperature at which this test is conducted. So, international codes of practice for design recommend temperatures of 30 degree lesser than the minimum service temperature to which the member is subjected. For example, the service temperature of a members below splash zone is 0 degrees. For example, these members, the service temperature is 0 degree. For members within splash zone, it is the lowest atmospheric temperature. Usually, it is about 20 to 24 degrees. Okay, usually. Okay, this is called atmospheric zone of corrosion. This is called splash zone, and this is called the immersion zone. Corrosion is maximum here. Okay, the service temperature here is about 20 to 24 degrees. The service temperature here is 0 degrees. Of course, the temperature here is 30 to 42 degrees. So, you must conduct Charpy's test at 30 degree below that minimum service temperature. Okay, because Charpy's impact index varies with temperature of conduct of experiments. Okay. Friends, very important point here. If you are using a member whose thickness is lesser than 6 millimeter, you do not require any impact test recommendations at all. Okay. Any material, any member whose thickness is less than 6 millimeter, no impact test requirement is suggested by the code. Okay. Now the question is, how do you measure this thickness? The thickness is not on the surface, it is through thickness of the member. So, we have something called through thickness stress. For members with loads applied normal to the surface, special steel with improved through stress thickness is required. Okay. You cannot have the thickness variation along its section of loading dimension. Okay. So, there are very stringent requirements which are advocated by the international codes for steel to be used as construction material for maritime structures. Having said this, let us talk about application of stainless steel for topside. So, we can recollect now what is a topside. Topside is a part of the superstructure where the members are above water, and usually topside consists of electromechanical equipments, living quarters, heli deck, drilling derrick and other pieces of elements and members required for oil and gas exploration if it is an offshore structure. If it is a coastal structure, topside actually has rails, gantry, crane operators, etc., which is going to happen on the deck. So, stainless steel can also be used as construction material for topside. One specific grade of stainless steel, which is called type 316 duplex grade steel, which is an higher alloyed special grade of stainless steel, are used where there were proof of they being used in North Sea in topside construction, downhole oil flow applications. There are very specific reasons why they have been used in specific applications. They have very good corrosion resistance, very high strength and very good heat resistance. Stainless steel, friends, offers a maintenance free, lightweight, fire and explosion resistance, which is very good for blast walls, cable ladders and walkways, because these are all the elements of the structural members which are more prone to blast, fire and explosion loading. Okay? Blast walls, cable ladders, walkways. If they can be maintained with a better grade of steel, higher corrosion resistance and fire and explosion proof, then accessibility, mobility of people during this kind of emergency becomes slightly practical and feasible. Therefore, stainless steel is recommended for these kind of applications. Stainless steel further possesses high life cycle benefit, and there is weight savings in the overall construction of topside structures. They also possess resistance to corrosion at higher temperature. In downhole gas and oil flow systems, stainless steel offers benefits facilitating the flow of corrosive products. Okay? So, if you are using it as a downhole oil flow pipeline, stainless steel have special advantages of corrosion resistance for these. Let us talk about the mechanical properties of steel and their variation, because mechanical properties of steel vary based on their chemical composition, heat treatment and manufacturing processes. I can give you an example. If you say mechanical properties of steel, let us say yield strength, ultimate strength, modulus of elasticity, we may not be studying this in detail with respect to the chemical composition, heat treatment and manufacturing process. Metallurgists will appreciate that they are dependent on these particular factors, but structural engineers in land based construction do not encounter this kind of variation in these mechanical properties. However, friends, when you want to use steel for maritime construction, it is important that we must understand the properties of steel, as these factors affect them very significantly. Furthermore, friends, as I said in the beginning, steel can be alloyed to change its engineering properties. The addition of alloy changes the behavior of steel under certain conditions. For example, manganese, niobium, vanadium can affect and compromise weldability. However, they increase ductility and toughness. So, important mechanical properties can also be altered by changing the alloying elements of steel. Manganese and niobium can increase ductility and toughness, but weldability is compromised. Sulfur enhances ductility, nickel improves toughness. It is therefore important to arrive at carefully balanced chemical composition to achieve the desired structural characteristics. That is a very important statement as far as steel choice for maritime structures are concerned. Heat treatment and manufacturing processes can also significantly alter the performance of steel under loading conditions. The geometric forms like rolled and formed steel shows higher strength, but if you increase the thickness of them, it reduces yield strength. Further, if you heat treat steel deployed in steel manufacturing sectors, they will also change the strength and toughness of steel to be used for maritime structures. So, friends, mechanical properties are not simple numbers, are not simple indicators which are useful for design. They are dependent on various factors, and the alloying elements also change these characteristics significantly. So, we need to maintain a balanced chemical composition of alloying elements while we manufacture steel and apply them for maritime structures. As we said, manufacturing processes figure out difference in strength. Let us see how do they affect the strength of steel, or how manufacturing process can become or can influence strength dependence. The common manufacturing process which are used for steel manufacturing are the following: as rolled, normalized, normalized rolled, thermomechanical roll, what we famously known as TMR, and quenched and tempered steel called as Q&T. You must have heard this kind of steel with their brands associated in India as well as in international market. TMR is most commonly and popularly used for high grade, high strength steel. Steel cools as it is rolled with a typical rolling finish, and the temperature is about 750 degrees Celsius. If it is allowed to cool naturally, then it is called as rolled steel. Normalized steel is manufactured by heating as rolled steel up to 900 degrees Celsius. At the temperature, it is held for specific time before being allowed to cool naturally. That is a normal manufacturing process. The normalizing refines the grain size and increases toughness. Normalized rolled steel is manufactured by rolling the steel at temperature above 900, which eliminates the extra process of reheating of steel. Therefore, friends, normalized and normalized rolled steels have a designation called N. Whenever you see a steel grade designated with N, it is indicating normalized and normalized rolled steel as a group. Thermomechanically rolled steels, what we call as TMR, is manufactured at a lower rolling finish at about 700 degrees Celsius, whereas N grade steels are manufactured at 900 degrees Celsius. Okay? So, M grade is what we associate with TMR, mechanically rolled. They are done at 700 degrees Celsius, whereas quenching and tempering steels, what we call as Q&T grade, quenching and tempering steel, is manufactured at about 900 degrees Celsius, which is rapidly cooled. Friends, N grade cooled gradually, M grade no cooling necessary, whereas Q&T grade rapidly cooled. This is what we call as quenched. Okay? And when you see this kind of grade, they have got low toughness but high strength and hardness. They are classified as Q grade. So, N grade, M grade, Q grade. Okay? Quenching involves cooling a product rapidly by immersing this product directly into water or oil. Tempering is the next stage of heat treatment to temperatures below authentic range, which softens the steel. So, when you do quenching and tempering both, then it makes the steel tougher and more ductile. So, use of high tensile steel can reduce volume of steel, no doubt about that, but steel needs to be tough at operating temperatures. So, we are now looking for properties other than yield strength, which is indicated as sigma y, Young's modulus, or I should say modulus of elasticity, which we call as E. Generally, the steel which we remember is 2.1 10 power 5 Newton per mm square, and this varies anywhere from 450 to 600 Newton per mm square. That is 415 to 600 Newton per mm square. So, these are the two properties generally we look at while we choose steel for onshore construction, but in offshore we also look for the grade and type of manufacturing like N grade, M grade, Q and T grade. We also look for the properties like ductility, toughness, hardness at service temperature and very high temperatures. So, friends, in maritime structures, before we choose a material for construction, we examine these properties at different temperature dependence also, which is a very interesting factor and new to learn compared to the steel being used in onshore construction. If you look at higher strength steel, though higher strength steel can reduce the volume, but you need to have enough toughness and strength. For this, higher strength steel can be achieved by toughness and ductility improvement, and they can be achieved by low carbon steel manufactured using thermomechanical rolling process. So, TMR is a manufacturing method, low carbon is a composition of carbon in steel. So, low carbon steel manufactured using TMR technique can arrive to be high strength steel, which has got relatively a higher toughness and ductility, which is commonly used in maritime structures. Look at this table, which is quite interesting. I am now classifying yield strength based on thickness. This is very interesting product information which was not known to us as a designer if you do not choose steel for maritime applications. If you look at grade S275 steel, the 275 number refers to yield strength, which we all know, but this refers to yield strength of thickness lesser than 16 millimeters. If we choose a member whose thickness is more than 16 up to 40, or even more than 40 up to 63, or even more than 63 up to 100, the yield strength keeps on changing, friends. Okay? For the same grade of steel, the yield strength keeps on changing for design applications. Okay? That is a very interesting point which we must note. Furthermore, the tensile strength also varies for respect to the thickness. Having said this, the table gives us information about the minimum yield strength required for hot rolled steel based on the structural design used for and recommended by Eurocode and British standards. The letter S in this grade is referring to carbon steel. Okay, S refers to carbon steel. The minimum yield strength and tensile strength are only taken as the design parameters for carbon steel for designing them for various applications. So, if you look at this particular curve, which is a stress strain curve. I am just comparing different grades of steel for our information. Okay. Look at the stainless steel, which I am now marking on the screen. Okay. There is no initial yield strength or yield point. Therefore, you draw a tangent to the initial straight line parallel at 0.2%. 0.2%. It is 0.2 by 100, is it not? Therefore, 0.002. Draw a line parallel to the initial tangent. These two lines are parallel. Wherever this line is intersecting, that becomes my yield strength. Okay, that becomes a yield strength. It's called proof strength. So, stainless steel has got a proof strength about 420 megapascal, whereas stainless steel of different grades of 204, of 204, 360 and carbon steel of A36, which I am marking here, of A36. Okay. They have a strength only up to 280 megapascal. So, friends, please note that all stainless steel grades do not have higher strength. It varies with its composition, manufacturing processes and alloying elements. Okay. So, that is the important information we have. Now, friends, let us come to the summary of this lecture. In this lecture, we focused on understanding steel as one important application material for maritime construction. But steel as a general term cannot be loosely used. Steel has got physical, mechanical and engineering properties which need to be elaborated if you want to choose them for maritime application. They are classified based on different methods. There are about 8 classifications, there are about 3 groups. And you will surprisingly see some of them are grouped based on yield strength, some of them are grouped based on toughness, some of them are otherwise grouped based on strength itself, tensile strength. Okay. So, one should be very careful in designating steel based on its manufacturing process, okay, like N grade, M grade, Q and T grade and so on. So, the manufacturing process can also alter the engineering properties of steel to the desired value. So, friends, this lecture gives a very good insight about information related to choosing steel, understanding its classification in line with the international codes like American Bureau of Shipping, ASTM standards and also API codes of practice, which are used commonly as design codes for design of offshore structures, and nevertheless offshore structures are subsets of maritime structures. I hope you followed the lecture. For further materials, please refer to the references listed in the SwayamPrabha course of this specific course. If you have any queries, please post them by email to us in the discussion forum. Instructors will be able to answer your queries in an elaborate manner to reinforce your better learning and making interest and developing interest in this. Please continue to stay, listen to all other lectures following by this and you will get good information, and this is a very professional course which can give a very good job opportunity in maritime industry, maritime sector in the coming future. Thank you very much. Namaste.